you.
Yeah.
So, good morning to everybody. So today I'm very happy to have with us Ruijun Wu, that is a new postdoc here in Sissa. He will do a seminar on super Liouville equations, existence on closed Riemannian surfaces.
Okay. Thanks for the introduction. Yeah, I said, I'm a new postdoc here. Just arrived last month. I would be very happy to meet you guys once possible, but nowadays it's hard. So I just gave a seminar to introduce my my work in the last 2 years or so, and we hope to have an introduction of myself to our community. So I'm going to talk about this super Liouville equations. Seen from the name, it's quite physics, but actually the kernel part is mathematics, and actually I rely heavily on the analysis, meaning the estimates on all kinds of, for example, the Morse Thm I estimates and the estimates for the Dirac operators. Yeah, okay. So in my talk, the first part, I will briefly describe the model, and there are some physics background, but well, this is just the motivation of the problem. And after formally introduce the problem, we will come to the mathematical part, and in the end, I give a sketch of the proof. So let's start. I mean, we are going to talk about super Liouville equations, but what does this mean? So first, let's briefly recall what is Liouville equations. This dates back, of course, to Liouville, actually long time ago. At that time, Liouville want to study a constant mean curvature surface whose domain is essentially the complex plane. He studied this equation. This was the very originate of this whole field. To put it in the modern language, this is the prescribing curvature problem, meaning that, let's talk about the two-dimensional case. Give me a surface M2 with a metric G, and the Gaussian curvature is Kg. Then, taking a scalar function U, the Gaussian curvature of the conformal metric e to the power 2u times g is given by this, e to the minus 2u times kg minus Laplacian u. In another way to put it is this way, like minus Laplacian u equals k tilde e to the 2u minus the Gaussian curvature. K tilde here is the function which is the the curvature function which you want to prescribe. Well, the problem is goes like this: having a surface mg and having a function. I'm asking whether this k tilde could be a curvature function or not, which is equivalent to say that whether this equation is solvable or not. Well, there are very special cases. For example, k tilde is constant. This is of course solvable. This is given by the uniformization theorem. Of course, this constant should have the right sign because of Gauss-Bonnet theorem. But there are also cases where this is not solvable. Say, if k tilde is a scalar, it's a coordinate function or a translation of the coordinate function, this is never solvable. It's because of a Kasdan-Warner condition, if you know that. But anyway, I just want to give you the impression that well, this even in this old case, it's not always possible for function k tilde, but for constant one, it's always solvable. And later in my work, I will also restrict to the constant k tilde case. Well, a remark is that actually, even nowadays, on the sphere S2, what kind of a function can be prescribed as a Gaussian curvature function is still a research topic. Okay, coming to the physics side, this later the physicists when they developed quantum field, the field theory or even quantum field theory, they meet similar equations and they name this as the Liouville field theory. Briefly speaking, this is this goes in this way. You have a field which is represented by a scalar function phi, say defined on an open domain in the complex plane, which takes real values. Then the action on this field is given by this this one. So look at the first term is like gradient phi squared. It's a Dirac energy. And second is Q is a constant, R is a the scalar curvature, or twice the Gaussian curvature. Then the last one is lambda b, and again physics parameters. And here comes a nonlinear, exponential nonlinearity. This has several applications in physics. So just to mention some, it's one of the conformal field theory. And it's a special case of the Einstein equation, which characterizes the Liouville gravity. Well, it also describes some excited strings in the quantum string theory. And in higher dimension, it can also, I mean, in the theory of superconformal gauge theory, the equation also takes the same form. By this mean, I mean, it's named after Liouville because the Euler-Lagrange equation of such actions are actually of the form like Laplacian u equals some exponential of u. So it's Poisson equation of exponential nonlinearity. Well, okay, just to say, like in physics, there are several models which gives us the equation of Liouville type. Therefore, this is the reason why we should look at such kind of equations. Well, then we are going to consider super Liouville equations, which is from super Liouville field theory. What is that? This comes from the supersymmetric principle. Yeah. So what is that? It tells us that in this real world, there are two kinds of particles. One is bosons and one is fermions. Say bosons, I will take one boson field U and one fermion field psi, where the boson field U is a real valued function and psi is a vector valued function which take values in C2. For simplicity, we define them again on an open domain on the complex plane. And then they should satisfy this equation, this system. Laplacian u equals a e to the 2u plus b e to the u psi square. And then the interesting case is this equation of psi. It's gamma alpha partial alpha psi equals m e to the u psi, where a, b, and m are constant. Well, they have certain kind of physics meanings, but later I mean, we are going to set them to be constant, like 1 or -1 after our convention. Here, the gamma alpha are the Pauli matrices given here. And partial alpha are just the partial x alpha, the partial derivative in the coordinate directions. If you compute them, this gamma 1 partial x1 plus gamma 2 partial x2 acts on complex C2 valued function fh. It's given by -2 h ln z and 2 times the z bar derivative of f. So briefly speaking, this operator, this gamma alpha partial alpha, is given by this matrix operator, which consists of Cauchy-Riemann operators. We know that the Cauchy-Riemann operators are nice operators in the sense that they are elliptic, and we know a lot of about them. So I will write this as D last. This is the Dirac operator. This is the Euclidean Dirac operator. And now we want to define this in a proper way on a closed Riemann surface, not on a Euclidean domain. This is still possible, but this requires some topological conditions, which I'm going to tell you. So take a closed Riemann surface, then the boson field is easy. It's just a real valued function U. But then the fermion field psi now is not anymore just the C2 valued function. It's actually a section of a vector bundle S. This S is a C2 vector bundle. On this bundle, this is called the spinor bundle. And on this bundle, the important thing is that there is a Dirac operator B slash, which is locally given by the gamma alpha partial alpha just in the previous slide. So I will tell you more about this, but just now, just keep in mind that on this vector bundle, there is a Dirac operator D slash, which is a first order operator, which is locally given by the Pauli matrices. Then on this two field, we can define an action, which is given by this one. The first one is the Dirichlet energy. The second one is 2 times the Gaussian curvature, which is the scalar curvature, times U. That's linear in U, and then minus K tilde e to the power 2U, and plus this coupling. This d psi psi is the Dirac action, and minus rho EU psi squared, which is a coupling between U and psi. But this is just a simplification of the physics action, which I set a lot of parameters to be 1. But what I care about is this equation. The Euler-Lagrangian equation is given by this one. Laplacian U equals minus K tilde e to the 2U plus Gaussian curvature minus this coupling, and d psi equals rho e to the power U psi. This is Liouville type equation, and the second one is the critical Dirac equation. Critical in the sense that in the Sobolev sense, saying like if we start with the weakest Sobolev regularity, this doesn't fit into the bootstrap argument. This equation is strictly conformally invariant, but this action functional might be not. So it is infinitesimally conformally invariant, which is enough for physics. But if we check the strict conformal symmetry, it's only satisfied by this Euler-Lagrangian equation. But this is enough for us. As said, what we care most is about solution of this equations. And once we have a solution, we know the critical point of this. And this tells us that, well, without loss of generality, we can choose the right conformal factor such that this Gaussian curvature is constant. It's a uniformized one. It's either 1 or 0 or minus 1. I mean, in this talk, I'm going to concentrate on k equals 1 or k equals minus 1. But k equals 0 is something special because if you look at this equation, if k equals 0, which means the surface is the torus, and k tilde, you should set it to 0. But this equation becomes Laplacian U equals minus rho e to the power U psi squared, and which forces either psi equals 0 identically or rho equals 0, which decouples the system, which is not very interesting. So we will give 2 results on k equals 1 and k equals minus 1. And the aim of this talk is to find solutions of this equation, find some interesting solutions. Well, before
can I ask some questions? Sure. Already?
Sure.
It's Dabrowski here. So can you, okay. So you solve equation for U and psi, I understand, right?
U and psi, yes.
Okay. Can you remind, I mean, K of G is curvature, right? Or conformal? K of G is just the Gauss curvature, right?
Sorry, say it
K of
again.
G is Gauss curvature, correct?
Yes, K is Gaussian curvature.
But K tilde is a parameter here, or what is K tilde?
K tilde is a given function.
Okay.
And later I'm going to take it as a constant.
Okay.
Which have the same sign as K.
Okay. Okay.
Yeah.
Thanks.
Yeah. I mean, when K tilde is constant, this term e to the power 2U is anyway conformally invariant. That's the problem. The feeling of the strict conformal symmetry is this part. So on sphere, we have Mobius symmetry with the conformal invariant, but in other cases, this might not be true.
Okay, thanks.
Yeah. Okay, let's talk about this Dirac operator. I mean, I will give you more information because, I mean, having that Liouville function, what matters is actually the spectral behavior of Dirac operator, which is what I'm going to talk about here. So this, first, this spinor bundle, it's a C2, the fiber is C2, it's a C2 vector bundle. And on this bundle, there is a natural connection denoted by this one, which is a partial derivative, which tells you how to do partial derivative on this on sections of this bundle. And there are endomorphisms gamma EI, where EI is a local orthonormal frame, like partial x1, partial x2, such that this square to minus identity. So think about the Pauli matrix, which satisfies exactly this property. And once you have this, you can define the Dirac operator as gamma E1, partial E1, gamma E2, partial E2, which is the first order elliptic operator, which is also self-adjoint. And this tells you that.
Okay, sorry, can I again? So of
sure.
course, gamma of E1 anti-commute with gamma of E2, probably.
Yes, yes.
Okay.
Yeah, I should write it here, but yeah, I just didn't. What I want to emphasize is this.
Okay,
this.
Thanks.
Yeah. This ellipticity and self-adjointness tells us that it is the spectral is discrete. Of course, the manifold is closed, and moreover, it consists of three parts, like the lambda 1, lambda 2, which go to infinity, and lambda minus 1, lambda minus 2, which go to negative infinity, and it's symmetrical with respect to the origin. Lambda minus k equals minus lambda k. And there are also kernels. So the multiplicity of the kernel is denoted by H0. And then coming back to this linear-Rovich formula, it says that D square equals connection nabla star nabla plus scalar curvature over 4. Well, if you, this is a zero order term, we forget about this. This is the Laplacian. This tells us that the Dirac square equals Laplacian, which justifies the philosophy that the Dirac operator is actually a square root of the Laplacian. But we know that positive Laplacian operator is a positive operator, it's square root. The square root of a positive operator might, I mean, consist of two parts, like plus and minus. Yeah. Okay, this H0, which is the dimension of the kernel, it's a conformal, sorry. It's a conformal invariant. It depends on the spin structure. The spin structure is the structure which gives you the construction of the spinor bundle. But H0 is also invariant under conformal transformations of the metric. Therefore, like you remember that in the previous step, we did some conformal transformation to make the Gaussian curvature to be a constant. So this doesn't harm H0. For example, on the sphere, H0 is 0. By the way, the spinors which lies in the kernel of Dirac operator are called the harmonic spinors. Corresponding to the functions in the kernel of Laplacian operator are called the harmonic functions. So on sphere, H0 equals 0, which means there are no non-trivial harmonic spinors. Actually, this is even more true. On any Riemann surfaces, there exist spin structures such that H0 equals 0. So this is the case we are going to consider. I mean, I need H0 to be 0 to get some good estimates.
Yeah. Sorry, I have a question. I don't know what it means, the adjective spinor. What is a spinor bundle?
Sorry?
No, I don't know what is a spinor bundle. So
it's just the vector bundle.
Mm-hmm.
which on which there is a connection, covariant derivative, and there are like such kind of locally such kind of Pauli matrices.
Ah, okay. This is okay.
No, this is not the definition of the spinor bundle, but this is kind of a characterization of the spinor bundle.
Okay. Thank you.
So that what we need is just a vector bundle with the Dirac operator. And to define Dirac operator, we need this covariant derivative. We need this Pauli matrices locally, and sorry. Yeah, I mean, actually, this kind of thing we can extend it to more general vector bundles, not necessarily spinor bundles. But yeah, up to now, what we need is just a vector bundle which admits a Dirac operator satisfying this kind of spectral behavior properties. Okay.
Yeah. Thank you.
Yeah. So corresponding to this spectral behavior, we take the eigenspinors phi k associated to lambda k and phi 0j, which are the harmonic spinors. Note that the ellipticity tells us that this is finite. Okay, this is finite space, and they form an orthonormal basis of the L2 sections. And any psi, which is a L2 spinor, we formally expand it in this way. And the Dirac operator acts formally as it kills this part and put a lambda k in front of this phi k. And now we want to define S power of absolute value of Dirac, which is defined formally in this way. I mean, only formally. For those which make sense in L2, is defined to be the HS. So this is the Sobolev space we are going to consider. We are going to take this little s to be half. So anyway, this is the definition of the Sobolev space for the spinors. I mean, with respect to this spectral decomposition. And H minus S for negative index, this is the dual space, such as Sobolev space for functions. Well, this action functional. From now on, we are going to emphasize this role because it plays a role in our proof. So the Lagrangian equation is this, and as said, we are going to consider k tilde to be constant, which should have the same sign as the Gaussian curvature. And there are some very easy solutions. If you stare at this system, well, the first one is like the spinor field is 0. Well, this goes away, this goes away. This is just the old equation we know. And another kind of solution is U equals constant. So this goes away. These are constant, which forces the absolute value of psi is also constant. We call this the length function of the spinor. So these are constant length spinors. And on the surface, on the uniformized surface, we know on S2, we know they are again by killing spinors, but on other surfaces, it's at least I don't know. There's no more information about this. Again, if you require psi to be parallel, which requires rho equal to 0, which decouples this system, which well, it gives you some boring solutions. In this talk, we are going to look for some solutions which are not of this kind. There are some literatures, briefly speaking. There are the super Liouville equations, which starts from 2007, and then they have a lot of studies on this. But note that they choose some other, they choose this sign to be plus, and yeah, they also only find this kind of straightforward solutions, and then they did some blow-up analysis of this, like studying the compactness of the solution space. And for this Dirac, this kind of critical Dirac equations, there are also some work done by Isobi and Malito. And the Liouville type equations are, I mean, there are a lot of big guys in this field, like Kassan Warner, Struer, Zhang Yang, Dinh, Maggiodi. Well, a lot of measures are known in this field, and we are going to use some new result in this field to get a good estimate, such that we can get the solutions. Well, the main results are given as this. So this system, in case of genus 1, has solutions if rho is not in the spectrum. And the assumption is genus bigger than 1, H0 equals 0, and they are constant. As we said, this doesn't harm anything. The Gaussian curvature of the G equals -1 doesn't harm anything, but K tilde equals constant is some great simplification. And the H0 equals 0, we know that there are such surfaces. Another case is the sphere case. So automatically H0 equals 0 in this case, and again K equals 1 equals K tilde. And in this case, each eigenvalue of the Dirac operator is a bifurcation point, meaning that there is a sequence rho kj converging to lambda k such that the Euler-Lagrange equation with parameter rho kj has a non-trivial solution. These are joint work with Alex Tjevenica and Lea Macchiodi. They are both here some years ago. Yeah, I mean, in the remaining part, I'm going to give some brief, some sketch of the proof. Before that, so first, the solution is never isolated. It's never unique, because the spinor bundle has some intrinsic quaternion structure, which says once we find a solution with non-zero spinor, we immediately get a 3D family of solutions. So we don't expect for uniqueness, of course. Then it can also be seen as a weighted eigenvalue problem or eigenvalue problem. I mean, look at this equation is a weighted eigenvalue problem with weight e to the power u. But actually, if you make a conformal transformation of the metric G, then with respect to this metric, this is exactly an eigenvalue equation. And the third one is that on this spinor bundle, there is, if you compose gamma E1, gamma E2, this is globally defined, not only locally. And they anti-commute with the Dirac operator. Therefore, there is no loss of generality putting a minus sign here, if you care about this eigenvalue problem, because we require rho to be positive. But for the second equation, you can also take upside rho to be negative. But that's just some short remark. And then let's focus on the proof, the strategies, and the difficulties. The first thing is that, as we said, the Dirac operator has a very, very negative spectrum. This causes the functional to be strongly indefinite. And we have a lot of work on indefinite functionals like the Schrodinger operators, which allows for some kind of negative spectrum. But usually they are bounded and finite directions which are negative. But in this case, as we have seen, the spectrum of the Dirac operator is symmetric with respect to the origin. This means that there are infinitely many directions on which the function j goes down to negative infinity. And there are, so motivated from the classical theory, we also define some Nehari type manifold. Usually this Nehari type manifold is codimension 1 of finite codimension. And but in this case, we need some infinite codimension submanifold. This can kind of killing the negative spectra of the Dirac operator. And then the second difficulty is that there might be a large symmetry group. In particular, this is the case for sphere. And there is a non-compact Mobius group. And for the variational problem, we know that once we have a non-compact automorphism group, there cannot be very good estimate. And basically, there are always bubbles. And to kill this, we need a balancing condition called the center of mesh condition. This was originally used in the prescribing curvature case, but recently using under this condition, the analysis guys get some good estimate, and we are going to use it, and this helps a lot. So this center of mesh condition on one side limited this symmetry group, which overcome the difficulty caused by the non-compactness, and on the other side, it also gives us a very good estimate. And then in the genus, higher genus case, if rho is not in the spectrum, then we have mounting path. Locally, the functional satisfies some mounting path structure. If rho is small, then we can find mounting path solutions. On the other way, if rho is very large, then there are still negative directions, which makes the functional decrease. But in this case, we can find some linking structures, and therefore we find the linking solutions. This is not the case for the sphere. I mean, if we try the same strategy, it would not work for the sphere. Instead, so there are no mounting paths and no linking. This means that, well, we tried to find this, look for this, but we didn't find, and there are some evidence saying that there cannot be such kind of structures. Then we tried to argue by contradiction. So we use some Morse type theory to say that when rho is close to, there must be rho close to lambda k such that there exist non-trivial solutions. A final remark is that coupling in this case is also good for us. In particular, sign of rho, sign of the last term, like minus rho e to u psi square, is very important in this function. And there are works on the indefinite functionals, calculus, variational measures on this indefinite functionals by Robinovich, Benchi, Dean, Abondandolo. Usually they pose some restriction on the nonlinearity, which then, yeah, as far as I know, they don't fit into this super-Liouville framework. So we have to work by hand on this concrete problem. Well, let's look at the proof of theorem 1. I just gave the brief ideas. First, the functional is defined on this space, but there are a lot of negative directions for the functional. Therefore, I want to kill them. I put this condition. So P negative is the projection to the space spanned by the negative eigenspinors. So look at this. If u equals 0, the condition says that p psi minus rho psi project to the negative part is 0, which means psi lies in the linear span of the positive eigenvalues, eigenspinors, meaning that the eigenspinor associated to positive eigenvalues. So very roughly, this condition tells us that we kill almost all the negative directions in the functional. And the good thing that this subset is first a submanifold of this one, and also a natural constraint, meaning that well, the functional J rho defined on this total space has critical point, and J rho restricted to N rho has the constraint critical points. And it turns out that constraint critical points are also free critical points. So it's natural. In this case, we call rho a Nehari manifold, or Nehari type manifold. So this is a very good condition. I mean, first, it kills the negative direction. Second, it doesn't harm our variational structure. And moreover, it satisfies the Paley-Smith condition C. So it's almost perfect. And then let's look at the local structures. So very, very roughly, if you allow me to expand this by the Taylor expansion as 1 plus 2u plus 2u squared plus higher order terms. Well, I could make this strict because there are this kind of estimate called there are a lot of people doing the Morse Trudian inequality, and they can give us enough information how to make this strict. Formally, if we expand it in this way, and also this EU as 1 plus u plus u squared over 2, then we see that this minus 2u cancels each other. This 1 goes out. By Gauss-Bonnet, it's 2 pi genus minus 1, 4 pi genus minus 1. And then we are left with du squared plus 2u squared, which is the coercive part, locally coercive part. I mean, in this step, both u and psi are very small in the corresponding norm, like h1 norm, h-half norm. And then this Dirac action part is d psi minus rho psi. And then there is a negative term, or like we don't know sign of u. So there is a term when u and psi are small, this is of higher order, but when u and psi are big, this actually dominates. So locally, we see that this is coercive. If rho is very small, say it's below the first eigenvalue of Dirac, this is also coercive quadratic. And then we get this is of higher order, we don't care. So locally you get a parabola, which says this is locally the mountain pass structure. When rho is a little bit large, above any eigenvalue of this Dirac operator, then this is a saddle. But in this case, luckily, we can find some linking. So to say, we start from 0 and going along a very negative level set and forming a circle. So if we find either mountain pass or linking, we know plus the property in the previous slide, we know that we can find min-max solutions. So this roughly gives us the non-trivial solutions. But we were not go into detail about this. These are purely estimates, and so this is a proof of the first theorem. And then coming to the sphere case. So if we try about the previous strategy, we find that it doesn't work. So do the same thing. Expand this using the Taylor expansion of this and this. So it turns out to be this one. Note that in the sphere case, we have to choose k and k tilde to be +1. Therefore, there is a sign difference to the previous one. So it's du minus 2u squared plus 2d psi minus rho psi minus 2 rho u psi squared. So this now become a saddle. And this is also a saddle. This is a saddle because in the sphere case, we know that rho has to be bigger than the first eigenvalue of the Dirac operator. Otherwise, there is no non-trivial solution. So this is some additional information. This is once proven by showing there is a Yamabe type invariant on the sphere, which tells us that rho has to be bigger or equal to 1. However, although they are saddles, and we know that there are finitely many negative directions, but there cannot be linking, as said. And moreover, we know the spectrum of the Laplacian on the sphere. So this integration by parts, this gives us the minus Laplacian u minus 2u and the inner product with u. So this spectrum of the Laplacian on the sphere is 0, whose eigenfunctions are constant, and 2, whose eigenfunctions are the coordinate functions, and 6, and blah, blah, they are the spherical harmonics. This 2 and this 2 actually is one of the difficulty or one of the problem which destroys the nice variational structures, because this 2 is exactly a eigenvalue of the Dirac operator, and recall that in the previous case we cannot deal with the eigenvalue case. We have to require rho to be not in the spectrum, and similar in this case. If the 2 lies in the spectrum, we don't have a good variational structure. So this was the problem, and how to deal with it. So to avoid this these 3 functions, we don't want such functions to appear as candidates for U. So we pose another balancing condition, which is given by the center of mass condition. The center of mass for given U, which is H1 function, W12 function, the center of mass for e to the power 2u is defined in this way. So S2 is canonically embedded in R3, and the X arrow is a Parisian function. But this is the, say, the physics center of mass. Well, e to the 2u is viewed as a kind of mass distribution. Then what we want to require is that the center of mass for u should be 0. And first, this condition, well, we can show that this condition can be imposed, meaning that this causes no harm of generality. And also, this controls the Mobius symmetry. This controls the non-compact group. And well, which was the trick also used in the prescribing curvature case, but in a different way. Another thing is that this actually gives some very good control on the U. So not only control the symmetry, but also control the H1 norm of U. And then the Nehari type manifold we are going to use is of this way. So first we kill the negative directions for the spinor. And second, we pose this center of mass condition. And third, we also pose this is a technical condition which is very convenient for us. Note that the integrand is actually e to the power 2u plus rho e to the power u psi square minus 1 is actually the right-hand side of the first equation for u. So if you have a solution, it's necessarily the integral of this one should be 0. Well, I will put several claims on this rho. First, it's a Nehari manifold, meaning that it's a submanifold and it's natural. And this restricted functional also satisfies the Paley-Smith condition. Moreover, since we killed infinitely many negative directions, and now we are only left with finitely many negative directions at the origin, like u equals 0, psi equals 0. So u equals 0, psi equals 0 is always a critical point, always a solution, very trivially. But we want to count, almost count the local index, if it makes sense. Well, this index changed because, I mean, the negative directions, whenever this rho goes from little to big, there should be some index change, which in turn indicates there should be some solutions bifurcating from this trivial solution. And this is actually the case. This can be, this index could be counted by some critical groups, which is a way to define this index. And then we detected the change of the critical groups, and then there are standard ways to show that there are actually bifurcations. Well, this is basically what I want to tell you. And there are, of course, the other cases like rho in eigenvalue, or for the sphere case, the bifurcation picture, the global bifurcation picture is still unclear. In the high Dirac case, the eigenvalue case is unclear to me. And they are, I mean, in physics, the super Liouville equations, they study this from a nontrivial point. Like they care about where giving an initial data, whether you can develop it in space-time. But in mathematical case, in this case, we care about like a fixed space-like surface and whether there are solutions. So there are not too much known about such problems. This was actually the first non-trivial solutions for the super Liouville equations. Except that in the domain, in the Euclidean case, in physics, there are several solutions which are known. Well, that's all. That's all I want to tell you. Thanks.
Thank you, Ruijun, a lot for your seminar. Now it's the moment if there are for questions. If there are some questions, you can ask directly.
Can I ask still another one?
Sure, sure, sure.
Just about this Möbius. So these Möbiuses are transformations of sphere of it, or of a surface, right? Of a sphere, for instance, right? But they are conformal transformations. In that case, by symmetric group, you mean transformations of the space on which you have these fields, not transformation of fields themselves, right?
Yes, yeah. I mean, this Möbius group on one side is the transformation of the sphere, but on the other hand side, such kind of transformations are actually conformal transformations of the sphere.
Right, so they are conformal transformations. So for a sphere, for instance, this could be instead of SO3, it could be SO41.
They also induce conformal transformations on the fields.
Okay, okay. But induce it from the transformations of the manifold, of the space, right? They are just lifts of these transformations to fields.
I took the wheel point as like we fix the base manifold and will these transformations as acting on the fields.
Okay.
Yeah.
Okay.
Okay, it seems to me that there are no more questions, so we thank Ruijun again, and we meet, if you want, next Friday.
Thanks.
Thank you.